Cruising down Interstate 95 at 70 miles per hour, your steering wheel suddenly turns to concrete. The engine temperature needle redlines in seconds. The battery light frantically flashes. Your car dies at highway speed. The culprit? A single, violently snapped strip of rubber. Back in the 1960s, a look under the hood revealed a safety net, up to 5 independent V-belts. If one broke, your water pump or alternator might still survive, allowing you to limp home. Today, that entire billion-dollar ecosystem of redundancy has been completely wiped out, replaced by one solitary serpentine belt. Why did the entire automotive industry deliberately strip away every backup plan, betting your life and the engine's survival on just one centralized point of failure? This isn't just a story about a car part. This is the brutal engineering war that reshaped every engine on Earth in the ruthless collapse of a massive global manufacturing empire. Detroit in the 1960s and early 1970s was a kingdom built on heavy steel, cheap gasoline, and mechanical excess. It was the golden age of the American muscle car and the sprawling family cruiser. To open the massive heavy steel hood of a 1969 Chevrolet Impala or a Ford Galaxy was to gaze into a cavernous metallic cathedral. The V8 engines were colossal, but they did not sit alone. Flanking these iron blocks was a sprawling, chaotic jungle of rubber and steel pulleys. This was the undisputed era of the V-belt. First invented in 1917 by John Gates, the V-belt was a marvel of early industrial engineering. Viewed as a cross-section, the belt was shaped like a trapezoid or a V. As it wrapped around a metal pulley, the tension would pull the belt deeper into the matching V-shaped groove of the wheel. The harder the engine pulled, the tighter the rubber wedged itself into the metal. It was simple, brutal friction at its finest. For over 50 years, this wedge action design was the lifeblood of automotive power transmission. But as cars grew more luxurious, they required more accessories. By the late 1960s, a standard American V8 engine didn't just need a belt to spin the water pump and the cooling fan. It needed an alternator to power the radio and headlights. It required a power steering pump to help drivers maneuver 2 tons of steel. It demanded a heavy-duty air conditioning compressor to keep the spacious cabins cool in the summer heat. Sometimes, an entirely separate air pump for early emissions control was added to the mix. The solution to powering all these new accessories was brute force redundancy. Automotive engineers simply added more belts. A fully loaded vehicle would often feature up to 5 distinct, independent V-belts snaking across the front of the engine block. Each accessory had its own dedicated rubber loop connecting it directly to the main crankshaft pulley, which sat at the bottom of the engine like a spinning distributor of mechanical wealth. For the American driver, this system offered a profound, almost comforting sense of security. It was the ultimate safety net of redundancy. If you were driving down a lonely highway in the dead of night and the belt powering your air conditioning compressor snapped, you merely rolled down the window. If the power steering belt broke, your steering wheel became heavy and stubborn, but you could still drive, even if the alternator belt shredded. The car's battery held enough reserve charge to keep the spark plugs firing until you reached the next town. Only the loss of the water pump belt meant immediate catastrophic overheating. In a world of 5 belts, losing one was an inconvenience, not a death sentence for your journey. However, beneath this veneer of driver safety, the multi-belt system was an absolute nightmare of manufacturing and maintenance. On the frantic assembly lines of Detroit, workers had less than a minute to install and tighten a web of rubber. Because each belt ran on a separate track, the main crankshaft pulley had to be stacked outward, extending deep into the front of the engine bay. The engine grew longer, demanding even more empty space under the hood. Furthermore, V-belts required manual tensioning. They did not have the elasticity or automatic spring-loaded tensioners of modern systems. To install an alternator belt, a factory worker or a neighborhood mechanic had to wedge a heavy steel pry bar between the iron engine block and the delicate aluminum alternator housing, physically pulling the unit backward using raw body weight to pull the rubber taut. Once the tension felt right, a purely subjective measurement based on the mechanic's intuition, they would blindly tighten a locking bolt to hold it in place. If the mechanic guessed wrong and left it too loose, the rubber would slip against the metal under heavy load. This slippage produced the defining soundtrack of the era, a high-pitched, ear-piercing squeal that echoed through suburban neighborhoods on cold mornings as cars fired up. If the mechanic pulled it too tight, the extreme tension would violently destroy the delicate internal bearings of the water pump or the alternator within a few thousand miles. The logistical bloat was equally staggering. Because each vehicle model, engine size, and accessory package required different belt lengths, auto parts stores and dealership warehouses had to stock hundreds, sometimes thousands of different V-belt sizes. The walls of every repair shop in America were draped in endless black loops of rubber, representing millions of dollars tied up in static inventory. The most fatal flaw of the V-belt, however, was a strict rule of physics. It could only bend in one direction. Because of its rigid trapezoidal shape, a V-belt could not be bent backward against its flat top. It could only loop inward. This meant a single belt could only wrap around 2, maybe 3 pulleys at most before the geometric angles became impossible to route. Engineers were trapped by this physical limitation. They had no choice but to keep stacking pulleys outward, adding more belts and demanding more empty air under the hood. In the early 1970s, this massive, redundant, and space-hungry system was the undisputed king of the road. It was bloated and arrogant, perfectly mirroring the American automotive industry itself. Detroit believed that they would always have unlimited space under the hood and unlimited fuel in the tank. They were wrong. A geopolitical storm was gathering on the other side of the world, and it was about to eradicate the luxury of space forever. October 1973. The golden age of American automotive excess did not fade away gracefully. It was violently assassinated. The Organization of Arab Petroleum Exporting Countries proclaimed an oil embargo, and overnight, the illusion of limitless, cheap gasoline evaporated. Across the United States, gas prices quadrupled. Panicked drivers waited in miles-long lines at dry filling stations. Almost instantly, the buying public turned their backs on the massive, gas-guzzling V8 land yachts that Detroit had spent decades perfecting. Consumers desperately demanded smaller, lighter, fuel-efficient vehicles. Japanese imports, previously dismissed as cheap novelties, began flooding the market. The American automotive empire was suddenly bleeding money and facing an existential threat. To survive, Detroit had to reinvent the automobile from the ground up. The mandate from the executive boardrooms was clear and brutal. Shrink the cars, cut the weight, and improve the fuel economy immediately. But there was a catch. American consumers still demanded comfortable, spacious interiors. They wanted smaller cars on the outside, but they refused to be cramped on the inside. To solve this geometric puzzle, automotive engineers adopted a radical redesign that would change the trajectory of automotive history. They shifted from rear-wheel drive to front-wheel drive, and they took the engine and turned it completely sideways. This was the transverse engine layout. By mounting a smaller 4-cylinder or V6 engine sideways between the front wheels, engineers eliminated the need for a long, heavy transmission tunnel running down the center of the car. It was a brilliant move for passenger comfort, allowing for a roomy cabin in a much shorter vehicle. But under the hood, this sideways orientation created a catastrophic mechanical crisis. In the old rear-wheel drive configuration, the front of the engine faced the car's radiator grille. There was a vast, empty canyon of space between the engine block and the front bumper. Stacking a massive, heavy crankshaft pulley that jutted out a foot from the engine to accommodate 5 separate V-belts was never a problem. But now the engine was rotated 90 degrees. The front of the engine no longer faced the empty grille. It directly faced the solid steel wall of the passenger side inner fender. The sprawling real estate of the muscle car era was gone. In these new compact front-wheel drive designs, the clearance between the front of the engine block and the unyielding metal frame rail was brutally tight, sometimes measuring less than 3 inches. The engineering departments at Ford, General Motors, and Chrysler hit a terrifying roadblock. The traditional V-belt system was mathematically and physically impossible to fit into this new architecture. If they tried to mount the standard multi-belt pulley system onto a transverse engine, the pulleys would literally punch through the steel fender of the car. There was simply no physical room to stack 3, 4, or 5 independent belts outward. The logical, immediate solution would be to strip the cars of their accessories. If there was no room for the belts, simply remove the air conditioning, the power steering, and the heavy-duty alternators. But market research showed this was commercial suicide. The American driver, even in a compact car, refused to sweat in the summer heat or wrestle with a heavy steering wheel in a grocery store parking lot. The accessories had to stay. The space, however, was gone. Detroit was backed into a corner. They had to power up to 5 heavy-load accessories, but they only had the physical space for exactly one belt track. Everything had to align perfectly on a single razor-thin plane right against the engine block. This was not merely a request for a new part. It was an engineering ultimatum. Automakers turned to their primary rubber suppliers, most notably the Gates Corporation, and presented them with an impossible mandate. They needed a single, continuous belt that was thin enough to squeeze into a 2-inch gap, yet strong enough to drive the water pump, alternator, power steering, and air conditioning simultaneously. Furthermore, because of the cramped, sideways engine bay, this single belt would have to snake its way around the accessories in a chaotic, zigzagging pattern. It would have to push, pull, and wrap around pulleys from both the inside and the outside of the belt loop. The executives in Detroit laid the burden of survival squarely on the shoulders of the rubber manufacturers. If a single belt system could not be invented, the new generation of transverse front-wheel drive cars could not be built. And if those cars could not be built, the American automotive industry would collapse under the weight of the fuel crisis. The survival of a billion-dollar industry now hung on a simple question: could anyone invent a rubber belt that defied the known laws of mechanical physics? The ultimatum from Detroit landed squarely on the desks of the Gates Corporation in Denver, Colorado. As the original inventors of the V-belt back in 1917, Gates was the undisputed titan of automotive power transmission. If anyone could solve the transverse engine crisis, it was them. Ford needed a single, ultra-thin belt system that could power every engine accessory simultaneously, and they needed it before the fuel crisis completely bankrupted the American auto industry. At first glance, the task seemed straightforward. Simply manufacture a much longer version of the traditional V-belt and weave it around all the pulleys in one continuous loop. But the engineers in the Gates testing laboratories immediately collided with an unforgiving wall of mechanical physics. A traditional V-belt was thick, rigid, and strictly designed to bend in only one direction. To navigate the chaotic, crowded real estate of a front-wheel drive engine bay, this new single belt could not just run in a simple circle. It had to snake through a complex labyrinth of metal wheels. It had to wrap over the top of the alternator, dive down under the power steering pump, pull tight against the water pump, and weave around the air conditioning compressor. To achieve this snake-like routing, the belt was forced to do something a V-belt was fundamentally never designed to do: bend backward. In mechanical engineering, this is known as reverse bending, and for a thick rubber V-belt, it is a death sentence. When a standard V-belt is forced to bend backward against its flat outer spine, the geometry of the rubber violently turns in against itself. The outer surface is stretched far beyond its tearing threshold, while the thick V-shaped inner wedge is brutally compressed and crushed. Inside the Gates testing chambers, the initial prototypes met catastrophic ends. Engineers rigged up massive electric motors to simulate the heavy rotational drag of a fully loaded car engine. They wrapped extended V-belts through the tortuous, serpentine-like paths required by Ford's new engine blueprints. When they hit the power, the results were disastrous. The immense friction generated by the reverse bending created a massive buildup of internal heat. Within minutes of running at high RPMs, the thick rubber would literally begin to boil from the inside out. The test chambers filled with the acrid, choking stench of burning polymers and vaporized synthetic rubber. As the structural integrity of the belts collapsed under the extreme thermal stress, they would loudly snap, shredding into hundreds of burning black fragments that violently ricocheted off the safety glass of the testing rooms. Physics was winning. The thick, trapezoidal profile of the V-belt, the very design that had reliably powered the automotive industry for over half a century, was the exact reason the new system was failing. The friction that gave the V-belt its gripping power was now generating the heat that destroyed it. The engineers at Gates faced a terrifying realization. They could not simply alter their flagship product. The V-belt, the foundation of their entire global empire, had reached its absolute evolutionary limit. To save the future of the automobile, they were going to have to invent something that had never existed before. If the thickness of the belt was causing it to tear itself apart, the logical solution was to make the belt thinner. But this presented a devastating paradox. A single belt in this new system was not just spinning a lightweight cooling fan, it was carrying the entire mechanical burden of the engine. It had to pull the heavy magnetic drag of the alternator, push the highly pressurized hydraulic fluid of the steering pump and crank the massive internal pistons of the air conditioning compressor all at exactly the same time. A thin, flat belt would easily survive the reverse bending, but it would completely lack the friction required to grip the metal pulleys. Under heavy load, a flat belt would simply slip, squeal, and burn away in seconds. The engineers needed a structural contradiction, a belt as thin and flexible as a ribbon, but with the aggressive, unyielding grip of a thick wedge. The breakthrough came when they stopped looking at the belt as a single V and started looking at it as a micro-landscape. Instead of molding one massive, deep rubber wedge that dug into a single channel, the Gates R&D team shaved away 70% of the belt's bulk. They created a wide, incredibly thin rubber band. Then, on the inside surface of this flat band, they engineered a series of tiny, parallel, longitudinal ridges. They called it the Micro V, or the ribbed V belt. It was a masterclass in surface area engineering. By replacing one deep groove with 5 or 6 shallow, microscopic ribs, the total contact area between the rubber and the metal pulley was actually increased, multiplying the gripping friction dramatically. Yet because the overall profile of the belt was less than 1/4 of an inch thick, it possessed unparalleled flexibility. The flat, smooth backside of the belt could now confidently roll over idler pulleys and bend backward without stretching, cracking, or generating lethal amounts of internal heat. Meanwhile, the ribbed inner side locked perfectly into the matching grooves of the accessory wheels, delivering massive amounts of torque without a hint of slippage. Back in the testing chambers, the new multi-rib prototypes were loaded onto the labyrinth of steel pulleys. The engineers powered up the dynos. This time, there was no acrid smoke. There was no screeching rubber. There was only a smooth, quiet hum. The new belt slithered gracefully through the complex array of wheels, bending inward and outward, wrapping around tight corners, and driving every single accessory simultaneously on a single razor-thin plane. Because of its winding, snake-like path through the engine bay, the industry would soon give it a permanent name, the Serpentine belt. Gates Corporation had successfully defied the physical limitations that threatened to kill Detroit's front-wheel drive revolution. They had created a mechanical miracle that fit perfectly into the cramped 2-inch gap of the new transverse engines. Ford had their single belt, but as the system moved from the controlled environment of the laboratory to the chaotic reality of the open road, a new hidden flaw emerged. The Serpentine belt was structurally perfect, but it was dangerously long, and heat was about to turn its length into a deadly liability. The Micro V Serpentine belt was hailed as a geometric triumph within the pristine, climate-controlled laboratories of the Gates Corporation. It had successfully solved the reverse-bending dilemma and fit perfectly into the impossibly narrow gaps of the new front-wheel drive engine bays. However, as the testing moved from the laboratory dynos to the brutal reality of actual engine prototypes, a catastrophic new flaw emerged. The problem was not the shape of the belt. The problem was its sheer, unprecedented length. In the old V-belt era, a typical accessory belt was a relatively short, independent loop, usually no longer than 30 to 40 inches. If the engine got hot and the rubber expanded, the belt might stretch by a millimeter or two, a negligible variance that the deep V groove could easily absorb. But a serpentine belt was entirely different. To navigate the complex labyrinth of the water pump, the alternator, the air conditioning compressor, and the power steering pump, this single continuous ribbon of rubber had to be incredibly long. Some early designs stretched over 7 feet in total length. When a 7-foot strip of synthetic rubber is subjected to the punishing 250-degree Fahrenheit ambient heat of an enclosed engine bay, the laws of thermal expansion are ruthless. Under extreme heat and heavy rotational load, the long serpentine belt naturally stretched. A mere 2% thermal expansion across a 7-foot belt translated to nearly 2 inches of physical slack. In the unforgiving world of mechanical power transmission, 2 inches of slack is a death sentence. As the belt lengthened, the microscopic ribs lost their aggressive bite against the metal pulleys. The results during the early road tests were terrifying. When a test driver slammed the accelerator to merge onto a highway, the sudden violent spike in engine RPMs caused the long belt to instantly stretch and whip. The slack allowed the belt to slip across the water pump pulley instead of turning it. The engine would overheat and critically fail in a matter of minutes. Furthermore, the old, traditional method of belt maintenance, Mechanics manually prying an alternator backward with a steel bar and locking it into place was completely useless. You could not permanently bolt down a 7-foot belt that constantly changed its length based on temperature and engine load. The belt needed to be tightened, but it could not be locked. The engineers realized they were missing a vital piece of the puzzle. The Serpentine belt could not survive on its own. It needed a dynamic, living companion. The answer was the automatic belt tensioner. Instead of bolting the accessory pulleys in fixed positions, engineers designed a heavy-duty, spring-loaded mechanical arm. At the end of this cast aluminum arm sat a smooth, free-spinning idler pulley. This wheel was strategically positioned to press firmly against the flat, outer backside of the Serpentine belt. Inside the housing of the tensioner was a massive, tightly coiled steel torsion spring. This was not a static piece of hardware. It was designed to breathe with the engine. When the car was started on a freezing winter morning and the stiff rubber belt was contracted, the tensioner spring yielded, preventing the belt from being too tight and snapping the delicate internal bearings of the alternator. When the engine reached operating temperature and the long belt inevitably stretched, the heavy internal spring instantly uncoiled, pushing the idler pulley outward to aggressively consume every millimeter of slack. When the driver stomped on the gas pedal and torque violently ripped through the system, the tensioner acted as a mechanical shock absorber, bouncing and flexing to keep the belt perfectly seated in its grooves. From a purely engineering standpoint, the automatic tensioner was an elegant, flawless solution. But in the executive boardrooms of Detroit, it triggered an absolute corporate war. The automotive manufacturing industry operates on fractions of a cent. If an executive can save 10 cents on a dashboard clip, they save millions of dollars across a production run. The automatic belt tensioner was not a 10-cent clip. It was a heavy, highly complex assembly requiring precision die-cast aluminum, high-carbon steel torsion springs, and sealed heat-resistant ball bearings. The bean counters and financial executives were horrified. Adding this expensive, heavy component to every single engine on the assembly line was a financial nightmare. They aggressively pushed back against the engineers. They demanded cheaper alternatives. They ordered the engineering teams to find a way to just bolt the belt tighter using the old manual brackets. A bitter standoff ensued between the forces of mechanical reality and corporate profitability. But physics, unlike human executives, refuses to negotiate. Every attempt to run the long serpentine belt without the dynamic spring-loaded tensioner ended in catastrophic failure. The belt squealed, shredded, or violently snapped, taking the engines down with them. The conservative automakers were backed into a corner. If they wanted to survive the fuel crisis by building smaller, space-efficient, transverse engines, they had to embrace the serpentine belt. And if they wanted the serpentine belt to actually work, they had to pay for the tensioner. The accountants ultimately surrendered. The expensive component was begrudgingly approved. The marriage of the Gates Micro V rubber and the heavy-duty steel spring tensioner was finally complete. The technology was no longer just a theoretical laboratory experiment. It was a fully realized road-ready system. The stage was now set for the ultimate gamble, putting this fragile, single point of failure into a mass-produced American icon. By the late 1970s, the American automotive industry was battered, bruised, and fighting for its life against foreign imports and fuel shortages. Ford Motor Company was preparing to launch one of the most critical vehicles in its history, the 1979 Mustang. Built on the entirely new downsized Fox platform, this vehicle had to bridge an impossible gap. It needed to satisfy the new fuel-conscious reality of the era, while still honoring the aggressive, muscular heritage of the Mustang nameplate. The buyers still demanded power. They wanted the legendary 302 cubic inch, 5.0-liter V8 engine. But the new Fox body architecture was drastically smaller, lighter, and far more aerodynamically constrained than the sprawling land yachts of the previous decade. Under the hood, the real estate was brutally tight. Ford needed a mechanical miracle to successfully package a massive iron block V8 and all of its heavy luxury accessories, air conditioning, power steering, high-output alternators into this newly shrunken engine bay. The experimental laboratories were officially closed. It was time for real-world application. The Gates Corporation and their newly perfected Micro V Serpentine belt system, paired with the controversial automatic spring tensioner, were called up to the major leagues. The 1979 Ford Mustang 5.0L would serve as the ultimate commercial proving ground. The true revelation of this technology, however, did not happen on the open highway. It happened under the harsh fluorescent lights of the Dearborn assembly plant. For decades, the engine dressing station on the factory floor had been a notorious bottleneck of manual labor. Workers routinely wrestled with heavy steel pry bars, straining their backs to physically pull alternators and power steering pumps outward. They had to manually tension 3, 4, or even 5 separate V-belts on every single engine block that rolled down the moving line. It was an exhausting, imprecise, and incredibly time-consuming industrial ballet. Suddenly, that entire chaotic, physically demanding process was completely erased. With the introduction of the new Serpentine system, the assembly protocol transformed. A worker simply took a single, flat, multi-rib belt and quickly routed it around the complex map of pulleys. Then, using a standard, long-handle wrench, they briefly torqued the heavy internal spring of the automatic tensioner backward. They slipped the final loop of the rubber belt over the smooth alternator pulley and simply let go. The tensioner's heavy cast aluminum arm violently snapped into place. The internal steel spring instantly absorbed all the slack. The belt was perfectly mathematically tight. What used to require several minutes of agonizing physical labor, guesswork, and multiple workers now took a single individual less than 15 seconds. It was a manufacturing revelation. On an automotive assembly line, time is the single most expensive commodity in existence. By stripping away 4 redundant belts and eliminating the manual tensioning process, the Serpentine system was suddenly saving Ford Motor Company millions of hours and millions of dollars in production costs. But the ultimate unforgiving test was the American consumer. When the 1979 Mustangs finally hit the showroom floors and rolled out onto the highways, automotive engineers across Detroit collectively held their breath. Would this single 7-foot-long strip of thin rubber survive the violent, twisting torque of a 5.0-liter V8? Would the dynamic, spring-loaded tensioner hold up against the blistering 250-degree heat of a Michigan summer traffic jam in the freezing depths of a Dakota winter? It did. The system operated flawlessly. When a driver hammered the throttle and the V8 roared to life, the tensioner arm performed a mechanical dance, visually bouncing and vibrating as it instantly absorbed the violent shock of the RPM spike, maintaining a perfect, unyielding grip. The microscopic ribs of the micro V-belt locked into the grooved steel pulleys without a single screech or slip. The engine bay was noticeably quieter, vastly more organized, and radically more efficient. The overwhelming success of the 1979 Mustang was a monumental engineering triumph for Ford and Gates, but for the rest of the industry, it was a signed death warrant. As the sales figures rolled in and the warranty claims for snap belts remained practically non-existent, a chilling realization swept through the corporate offices of General Motors, Chrysler, and eventually automakers around the globe. The traditional multi-belt system was rendered obsolete overnight. The era of redundant, bulky, space-wasting V-belts was officially over. There was no going back. The Serpentine belt was no longer just a desperate, experimental fix for cramped transverse engines. It was the undisputed future of all automotive manufacturing. However, this massive technological leap forward cast a dark, fatal shadow backward. The tipping point had been crossed. While Detroit celebrated their newfound efficiency and sleek, new engine bays, a profound economic tragedy was quietly unfolding across the manufacturing heartland. The mathematical reality was brutal. Transitioning from 5 belts down to 1 meant that the global demand for automotive rubber had just been slashed by 80% in a matter of months. The massive, roaring foundries and independent rubber plants that had spent half a century churning out millions of traditional V-belts were completely unprepared for the devastation that was coming. By the early 1990s, the automotive landscape had irreversibly transformed. What began as a desperate, space-saving necessity in the late 1970s had evolved into an uncompromising global engineering standard. From compact Japanese sedans to heavy-duty American trucks, the Serpentine belt was now the undisputed king under the hood. It was a towering triumph of mechanical efficiency, a victory for automotive packaging, and a massive leap forward for vehicle assembly. But in the gritty, industrial Rust Belt cities that supplied the auto industry, this technological miracle triggered a catastrophic economic earthquake. For over half a century, the production of traditional V-belts had supported a sprawling, highly profitable manufacturing ecosystem. Because the average passenger car required up to 5 belts, and because those rigid rubber loops wore out frequently and snapped without warning, the global demand for replacement belts was practically infinite. Entire factory towns in the American Midwest and beyond were built around the rhythmic, deafening thud of heavy steam presses and the pungent, unmistakable smell of curing vulcanized rubber. The mathematical reality that destroyed this empire was terrifyingly simple. By consolidating 5 independent belts into one single serpentine ribbon, the automotive industry instantly wiped out 80% of the volume demand per vehicle. The massive foundries that produced the V-belts were wholly unprepared for the brutal speed of this transition. For decades, manufacturers had poured billions of dollars of capital into highly specialized, heavy steel molds designed exclusively to cast the deep, trapezoidal shape of the traditional V-belt. These molds were massive, immovable monuments to the era of automotive excess. When Detroit, followed quickly by European and Asian automakers, abruptly canceled their massive supply contracts for multi-belt systems, these factories were left completely stranded. Within a span of just a few years, the deafening roar of the great rubber plants began to quiet. Assembly lines that once ran 3 continuous shifts, 24 hours a day, were abruptly throttled down to a crawl. The towering curing ovens, which had burned hot for decades to supply the world with a seemingly endless stream of replacement belts, finally went cold. Inside the sprawling distribution warehouses, a silent financial disaster was unfolding. Millions of brand new traditional V-belts, representing incalculable amounts of static capital, sat collecting dust on the shelves. The cars they were built for were slowly dying out in junkyards, and the sleek new vehicles rolling off the assembly lines didn't need them. The specialized steel molds, once the most valuable assets on a factory's balance sheet, were quietly hauled out to scrapyards and melted down for pennies on the dollar. The sheer scale of the industrial infrastructure that was rendered obsolete overnight was staggering. A massive engine of commerce was simply unplugged. The collapse did not stop at the major factory gates. The most brutal devastation occurred in the secondary economy, the vast, decentralized network of the automotive aftermarket. During the golden age of the V-belt, the barrier to entry for manufacturing replacement parts was relatively low. The trapezoidal belt was a simple, rudimentary design. Hundreds of independent regional suppliers and smaller manufacturing outfits could afford the basic rubber presses required to churn out generic replacement belts. These smaller companies thrived by supplying local auto parts stores, hardware shops, and independent neighborhood mechanics. If you walked into any garage in America in 1985, the ceiling was virtually guaranteed to be draped in hundreds of V-belts from a dozen different regional manufacturers. The Micro V Serpentine belt completely shattered this democratic manufacturing landscape. Producing a serpentine belt was not a simple matter of pouring cheap rubber into a heated mold. It was a highly complex, precision-engineered manufacturing process. The microscopic longitudinal ribs required to grip the pulleys without slipping demanded advanced, highly durable synthetic polymer blends. If the chemical rubber compound was slightly off, or if the internal tension cords were not perfectly aligned during the curing process, the long belt would stretch, fray, and violently snap under the immense load of powering every engine accessory at once. Furthermore, the heavy tooling required to cast the micro-rib surface was astonishingly expensive. It required computer-aided design, laser-cut precision molds, and entirely new multi-million-dollar automated production lines. The small and mid-sized aftermarket suppliers simply did not have the millions of dollars in capital required to completely retool their facilities. They were financially locked out of the future, unable to produce the new technology, and watching the demand for their old V-belt products plummet year after year, these regional suppliers began to hemorrhage money. A devastating wave of bankruptcies swept through the aftermarket supply chain. Family-owned manufacturing businesses that had successfully weathered recessions and world wars were suddenly liquidated. The local auto parts stores, which used to stock a diverse array of different brands, now only carried the high-tech serpentine belts produced by a few massive, consolidated mega-corporations who held the patents and the production capital. This was the ruthless, unforgiving nature of industrial progress. The optimization of the engine bay demanded a blood sacrifice, and that sacrifice was paid entirely in human capital. Tens of thousands of blue-collar jobs, machine operators, mold makers, warehouse logistics workers, and regional distributors were quietly erased from the economy. The automotive world celebrated the silent, smooth-running efficiency of the 1990s engine. But that mechanical silence was bought and paid for by the permanent silencing of hundreds of factories. The sprawling ecosystem of redundancy had been successfully slaughtered, leaving behind an industry that was leaner, highly consolidated, and totally dependent on a single, highly engineered strip of rubber. By the turn of the millennium, opening the hood of a brand new automobile revealed a masterpiece of streamlined engineering. The chaotic, tangled jungle of overlapping rubber loops that defined the 1960s and 1970s had been completely eradicated. In its place was a clean, highly organized mechanical landscape. At the front of the engine, weaving gracefully across a single, unified plane, was the Serpentine belt. It looked like the ultimate triumph of order over chaos. But beneath this sleek, hyper-efficient facade lurked a terrifying reality that the automotive industry rarely advertised. By consolidating the workload of 5 independent belts into one single ribbon of ribbed rubber, engineers had inadvertently introduced one of the most dangerous concepts in mechanical design into the everyday commuter car: the single point of failure. In engineering terms, a single point of failure is a part of a system that, if it fails, will stop the entire system from working. In the era of the V-belt, redundancy was the ultimate safety net. If you were navigating a treacherous mountain pass and your air conditioning belt snapped, you simply lost cold air. If your alternator belt shredded on a deserted midnight highway, your battery still held enough reserve power to keep the headlights shining and the spark plugs firing until you could safely pull into a distant gas station. Even the loss of a power steering belt was merely an intense upper body workout. The mechanical linkage of the steering column remained intact, allowing you to manually muscle the vehicle to safety. The Serpentine belt wiped that entire safety net out of existence. Because this single, continuous loop of micro V rubber was responsible for driving every single engine accessory simultaneously, its structural integrity became a matter of absolute life and death for the vehicle. When a Serpentine belt snaps, it does not offer a grace period. It does not allow you to limp home. It initiates a catastrophic, instantaneous domino effect that disables the vehicle entirely within a matter of seconds. Imagine driving down a busy interstate at 70 miles per hour in a modern, aerodynamically sealed sedan. Without warning, the Serpentine belt reaches the end of its fatigue life and violently tears apart. In the very first fraction of a second, the heavy magnetic resistance of the alternator is released. The dashboard instantly illuminates with a red battery warning light. Simultaneously, the hydraulic power steering pump stops spinning. The pressurized fluid that allows you to effortlessly guide 2 tons of steel with your index finger vanishes. The steering wheel instantly turns to concrete in your hands, demanding immense physical force just to keep the car from drifting into the adjacent lane. But the most lethal blow happens deep inside the engine block. The moment the Serpentine belt snaps, the water pump dies. Modern engines run incredibly hot, and they rely on a constant, pressurized flow of liquid coolant to pull that massive thermal energy away from the delicate aluminum cylinder heads. Without the water pump spinning, that cooling circulation stops immediately. The intense heat of continuous internal combustion has nowhere to go. It is violently absorbed by the engine's metal architecture. Within 60 to 90 seconds, the temperature needle will bury itself into the red zone. If the driver does not realize what has happened, if they panic, freeze, or try to push the car to the next exit, the aluminum cylinder heads will physically warp from the heat, the head gaskets will blow, and the internal components will seize. A $15 strip of rubber, failing at the wrong moment, can instantly destroy a $5,000 engine and leave a family stranded in the middle of speeding highway traffic. The industry had achieved perfect efficiency, but they had traded away all of the driver's margins for error. This radical shift in mechanical architecture fundamentally altered the psychological relationship between the driver, the mechanic, and the automobile. During the multi-belt era, drivers treated engine belts with a casual, almost dismissive attitude. It was an era of reactionary maintenance. You simply drove the car until you heard the high-pitched, obnoxious squeal of a slipping V-belt, or until one physically broke and was left dangling in the engine bay. It was a minor nuisance, easily fixed in a driveway on a Sunday afternoon. The Serpentine belt entirely destroyed that relaxed mindset. replacing it with a culture of deep mechanical paranoia and strict preventive maintenance. Because the consequences of a failure were now so absolute and financially devastating, drivers could no longer afford to wait for a warning sign. A faint rhythmic chirp coming from the front of the engine on a cold morning was no longer a minor annoyance. It was a terrifying countdown timer. Mechanics took on the role of automotive prophets, strictly advising customers to replace their serpentine belts every 60,000 miles, regardless of how healthy they looked on the surface. During routine oil changes, technicians began utilizing specialized flashlights and magnifying tools to inspect the microscopic valleys of the belt's inner ribs. They were hunting for micro-cracking, tiny, almost invisible fractures in the synthetic rubber compound caused by thousands of hours of heat cycling and extreme torque. If a mechanic found more than 3 cracks within a single inch of the belt, the entire system was deemed critically compromised and condemned to the trash bin. The responsibility of survival had been completely shifted from the vehicle's redundant design directly onto the owner's vigilance. This dynamic revealed a profound, unspoken truth about the trajectory of modern industrial progress. The public blindly accepted this single point of failure because the trade-off was brilliantly disguised. By trusting their lives to one vulnerable strip of rubber, drivers were rewarded with incredibly quiet cabins, drastically improved fuel economy, and engines that required practically zero daily tinkering. We happily signed a devil's bargain with the engineers in Detroit and the rubber scientists at the Gates Corporation. We agreed to surrender our mechanical safety nets in exchange for frictionless, optimized convenience. We accepted that the modern machine is a high-wire act, capable of breathtaking performance and efficiency, but entirely dependent on the flawless execution of a single, highly stressed component holding the whole act together. The Serpentine belt had conquered the world. It had bankrupted the aftermarket V-belt empires, silenced the deafening roar of the heavy rubber foundries, and forced a new era of hypervigilance upon the global driving public. But as it turned out, the space that this single belt saved under the hood was about to be filled with something that would change the world of automotive safety and performance forever. The transition from the traditional V-belt to the Serpentine system was characterized by brutal economic destruction and a terrifying centralization of mechanical risk. Tens of thousands of manufacturing jobs were wiped out, and the global driving public was quietly forced to accept a single point of failure under the hood. Yet despite this high human and mechanical cost, the automotive industry never looked back. To understand why Detroit, Tokyo, and Stuttgart so eagerly embraced this ruthless new reality, one must look not at the rubber belt itself, but at the empty space it left behind. In the highly competitive world of automotive design, there is a concept known as packaging. Packaging is the complex, three-dimensional geometric puzzle of fitting a massive internal combustion engine, thousands of feet of electrical wiring, plumbing, and safety equipment into a visually appealing aerodynamic shell. Throughout the multi-belt era, packaging was a nightmare. The engine bays were held hostage by the sprawling, outward-stacking network of V-belt pulleys. When the Micro V Serpentine belt arrived and successfully collapsed that entire chaotic network into a single 2-inch vertical plane against the engine block, it was as if someone had unlocked a vast new continent of untouched real estate. Automakers did not leave this newly reclaimed space empty. They used it to fundamentally revolutionize the modern automobile, unleashing a golden era of safety, performance, and technological integration. The most profound impact of this newfound space was on crash safety. In the 1980s and 1990s, federal safety regulations were becoming increasingly strict. Engineers needed to design complex crumple zones, sacrificial metal structures at the front of the vehicle, designed to crush upon impact and absorb the deadly kinetic energy of a collision before it reached the passenger cabin. With the massive, jutting V-belt pulleys completely eliminated, engineers were finally able to push the entire engine block further back toward the firewall, or mount it transversely with plenty of clearance. This created a vital buffer zone between the front bumper and the solid iron block of the engine. The space that was once wasted on spinning rubber loops was now dedicated to saving human lives. When a modern car is involved in a severe frontal collision, the engine bay collapses perfectly, keeping the passengers safe. This life-saving geometric architecture is only possible because the Serpentine belt got out of the way. Furthermore, the late 20th century saw an explosion of complex computer and safety technologies that all demanded physical housing under the hood. The anti-lock braking system, ABS, which revolutionized vehicle control on slippery roads, required the installation of heavy, bulky hydraulic pump modules. The introduction of multiple airbags required sophisticated crash sensors, advanced wiring harnesses, and secondary power modules. Stricter emissions standards mandated massive catalytic converters and complex exhaust gas recirculation, EGR plumbing. In a traditional V-belt equipped engine bay, there simply would not have been enough physical room to mount these critical new technologies. But thanks to the hyper-efficient packaging of the Serpentine system, engineers could seamlessly tuck ABS modules, ECU computer boxes, and advanced emissions hardware into the corners of the engine bay that were previously obstructed by redundant belts and manual tensioning brackets. The performance landscape was also forever altered. As consumers demanded better fuel economy without sacrificing horsepower, automakers began turning to forced induction, specifically turbochargers. Turbocharging an engine requires a massive amount of underhood plumbing, including air intakes, exhaust routing, and bulky air-to-air intercoolers to chill the compressed oxygen. The Serpentine belt's incredibly slim profile provided the exact margins of clearance needed to snake this complex turbocharger, piping past the engine block. Today, nearly every major automaker relies heavily on turbocharged, small displacement engines to meet global efficiency standards. This entire mechanical paradigm is fundamentally built upon the spatial efficiency of the Serpentine belt. Ultimately, this single strip of ribbed rubber became the silent, forgotten enabler of the modern automotive order. It is the invisible workhorse that carries the entire mechanical burden of the vehicle, yet it is buried deep within the dark recesses of the engine bay, completely ignored until the moment it fails. We marvel at our anti-lock brakes, our climate-controlled cabins, our fuel-efficient turbochargers, and our 5-star crash safety ratings. We praise the software engineers and the aerodynamicists. But beneath all of that luxury, safety, and computing power, the fundamental laws of mechanical rotation still apply. All of these advanced systems are entirely reliant on the brutal, analog friction of one thin ribbon of synthetic rubber gripping a set of steel wheels. The Serpentine belt did not just save the front-wheel drive car, it funded the space for the entire technological revolution that followed. To fully comprehend the magnitude of the Serpentine revolution, one must step away from the grease and steel of the engine bay and look upward into the corporate boardrooms where the future of the automotive industry was being decided. The story of the Micro V belt is not merely a tale of mechanical ingenuity. It is one of the most profound and ruthless examples of corporate self-destruction ever recorded in modern industrial history. At the center of this financial paradox was the Gates Corporation. By the early 1970s, Gates was sitting on an undisputed goldmine. Having invented the original rubber V-belt in 1917, the company had spent half a century building a global monopoly on automotive power transmission. Their business model was a masterclass in highly profitable, predictable obsolescence. Because every American car rolling off the assembly line utilized up to 5 separate belts, and because those belts were designed to wear out and snap, the recurring revenue stream was virtually infinite. Gates was producing millions of replacement belts every single year. They owned the factories, they owned the distribution networks, and they essentially owned the aftermarket. The traditional V-belt was the ultimate golden goose. Then came the 1973 oil embargo, the shift to transverse engines, and the desperate ultimatum from Ford Motor Company. Detroit needed a single Serpentine belt to save the front-wheel drive car. When the engineers at Gates realized that the multi-ribbed Micro V belt was the only mathematically viable solution to Ford's space crisis, the executive leadership was forced to confront a terrifying financial reality. If they successfully manufactured this single, durable Serpentine belt, they would be actively destroying their own market. By consolidating 5 belts into one, Gates would instantly annihilate 80% of their own volume demand per vehicle. In traditional corporate culture, this is considered financial suicide. A company does not willingly invent a product that renders its most profitable division obsolete. The natural instinct of any massive corporation is to protect the status quo, to lobby against change, and to milk the existing cash cow until it runs completely dry. There was undoubtedly immense internal friction. Sales executives and financial analysts stared at projections that showed their massive, global V-belt foundries going completely dark. But the leadership at Gates understood a brutal, unforgiving law of modern capitalism. If you do not cannibalize your own product, your competitors will happily do it for you. The executives knew that the transverse engine was the inevitable future of the automobile. The space under the hood was never coming back. If Gates refused to develop the Serpentine belt to protect their V-belt profits, a rival rubber giant like Goodyear or Dayco would eventually crack the engineering code. If that happened, Gates would not just lose a portion of their market share, they would lose their entire empire. They would be left producing millions of trapezoidal V-belts for a dying breed of older cars, while their competitors owned the future. Faced with this existential threat, Gates made the hardest choice a business can make. They chose to burn their own empire to the ground in order to build a new one. They poured massive amounts of capital into the research, development, and proprietary tooling required to manufacture the micro V-belt. They partnered in the development of the automatic spring tensioners. They willingly closed down their older, highly profitable V-belt production lines and laid off their own workers. They engineered the very weapon that slaughtered their traditional business model. However, this staggering gamble resulted in a brilliant, calculated victory. By destroying the simple, easy-to-manufacture V-belt market, Gates replaced it with a highly complex, precision-engineered ecosystem. The Serpentine belt was incredibly difficult to produce. It required advanced synthetic polymer chemistry, laser-cut molds, and massive capital investments that smaller, regional competitors simply could not afford. Gates had effectively built a massive, impenetrable financial moat around their new technology. They traded sheer volume for absolute dominance. The mom-and-pop aftermarket suppliers went bankrupt, and the automotive world was forced to rely on the elite few who held the patents and the technology. Gates transitioned from being a supplier of cheap, disposable commodities to being the undisputed architect of a critical high-tech engine system. Today, as you drive your modern vehicle, you are surrounded by the legacy of that ruthless boardroom decision. The silent, smooth-running engine bay, packed with life-saving safety modules and fuel-efficient technologies, only exists because a rubber company in Colorado had the courage to destroy its own greatest invention. The Serpentine belt stands as a permanent mechanical monument to the harsh reality of industrial progress. Sometimes, true survival requires total sacrifice. The old empire had to die so the invisible empire could live. Let's go back to that disabled car sitting on the shoulder of Interstate 95, surrounded by the deafening blur of passing traffic. Underneath the hood, the engine is completely silent, critically crippled by a single, violently severed strip of rubber. When you look at that broken Serpentine belt, you aren't just looking at a failed automotive component. You are looking at the ultimate, uncompromising metaphor for the modern industrial age. The multi-belt era of the 1960s and 70s was built on the philosophy of resilience through redundancy. It was a time when machines were forgiving, when a mechanical failure was just a minor inconvenience rather than an immediate catastrophe. But as our demands grew, as we begged for smaller vehicles, strictly regulated fuel economy, colder air conditioning, and advanced life-saving crash structures, we forced the automotive engineers into an impossible corner. To give us the future, they had to ruthlessly strip away our safety nets. The Serpentine belt is a masterpiece of mechanical paradox. It is simultaneously the greatest packaging triumph in automotive history and its most terrifying vulnerability. It is a single, heavily stressed point of failure that we all blindly accept every single time we turn the ignition key. We willingly traded the messy, redundant safety of the past for the sleek, highly centralized efficiency of the present. Furthermore, the Gates Corporation proved a chilling reality about the brutal theater of capitalist evolution. Sometimes the only way to guarantee your survival in a changing world is to have the courage to destroy your own empire before someone else does. Progress, it turns out, does not always mean building something stronger or adding more armor. Sometimes true progress means stripping away all of your backups, putting all your faith into a single fragile thread and hoping it holds. Have you ever been left stranded on the side of the highway by a snapped Serpentine belt? Or do you remember wrestling with the old squealing V-belts of the past? Share your mechanical survival stories in the comments below. And if you want to continue exploring the ruthless engineering wars, the hidden economic collapses, and the forgotten industrial empires that built our modern world, make sure to hit that subscribe button. We will see you in the next chapter of history.